So, but if we go, that's only plus if you keep them together, not if you do the way I just described it. Right? Otherwise, it would be hard to say minus this plus this. Right. Okay. Just minus and minus, exactly. So now, when we looked at the formal charges, we saw that sometimes we could have different structures, but one is better based off of the either having the lower total formal charges, so 0 is better than 1 is better than 2, etc., right? And if we did have something that had a +1 and a -1, the negative had to be on the more electron negative atom. That was how we determined the best Lewis structure. When you had variations in the structure that fit the Lewis structure, we determined it through the formal charge and the formal charge rules, the two I just named. Okay. Now that leads us into talking about exceptions to the octet rule. Okay. So you could have different types of exceptions, and they can go from either direction. You could either have more than an octet or less than an octet. And generally, where would those be? When I'm referencing a structure, what part of the structure would I care most about on that?
The center atom?
The center atom, absolutely. The center atom, right? That's where that's going to matter. That's what we're talking about.
Mm-hmm.
Additionally, I could have unpaired electrons, right? So I could have one extra. So in other words, an odd number of electrons as opposed to only an even number.
Correct.
Okay, and that would be another type of exception we'll talk about. That's
Nitrogen
actually
can do that?
something you should be more familiar with from biological classes where you're looking at free radicals.
Right.
Right, and the scavenging of those free radicals, because it's extremely active, it will go around and it will do negative things to both DNA, protein, and anything else.
Mm-hmm.
Okay, so exceptions to the octet rules. We're going to look at odd electron species. What are those called? I just said it. Free radicals, right? Yes. Incomplete octets and expanded octets. And once again, these two will primarily focus around the center atom, right? Because that's where it matters. Okay, let's start with the odd electron species. Odd number of electrons. Nitrogen monoxide. So this has 11 electrons in its Lewis structure. Just to verify things like that. NO, right?
Right.
And what would the valence electron count be?
With 6 and the other one is 5.
6 and 5?
That's 11.
11.
Right.
Odd. That means they can't be paired.
Correct.
One has to be unpaired in that structure.
Mm-hmm.
Okay, just to keep that in context. Okay. So it looks something like this.
Why you took that down?
I know it's in there.
I know, I keep looking there too, because they put that one up.
I'm like,
They took that one down because they put that one up.
oh,
For some
really?
reason, they feel like you can't have two, I don't know.
Wow.
Maybe he took it home, I don't know. Maybe I have no idea. I just
Hopefully
know that
they
when they
did
put that one
something.
up, they took this one down. You can see the holes, right?
Yeah, hopefully they did something with it, not just...
Okay, so here's the structure. If I do a Lewis structure count of it, this is what it looks like, and you can see the unpair there. Any questions? I mean, does that invoke any thought process at all about this?
No. No.
None?
None.
Pretty
Oh.
straightforward?
Yeah.
Why is the 1 on the nitrogen side and not the oxygen side?
Yeah, center atom?
The oxygen has 6, so the atom has to be.
6 and 5, what else? What did I hear? More electron negative. The one more electron negative is going to have the greater electron density, so you'd put that here, right? Can I maybe do that with formal charges? Potentially. If I did it with formal charges, I'd just get 0 and 0 on this structure. What if I did it on the other structure? What if I put this one, so 5 minus 2 and 1 is 5 minus 3, and 1 and 1, 5 minus 5 is 0. 6 minus 4 is 2, minus 1 and 1 is 0. What if I flip? What if I put this here and these two there? Do I have 0, 0 formal charges, or do I now have formal charges? I could do that through the formal charge. But you also already know, just intuitively, that the oxygen's more electron negative than the nitrogen, so it's most likely it's going to have that other electron, and there'll be one lost on the nitrogen.
It doesn't matter the difference as long as one is more than the other one? Like, because I see that it's 304 versus the 3.44. But if it was 304 and the, I don't know, let's say 300, the 304 will still get it, even though it's slightly different.
Well, just do the formal charge. Go ahead, Efren.
Oh, okay.
Were you here on the last lecture? No, got to look it up. Don't have time to go back. That's the problem. That's why we did it on Tuesday. I don't want to. It's not that I don't want to do it. I don't have time to do it. Right, and get through. That's important. So go back. Make sure you understand what formal charges are. I'll quickly state the formal charge is looking at the atom, taking the valence electrons, subtract out any individual electrons associated with it, and then subtract out 1/2 of any bonded electrons. Okay, so real quick, nitrogen has 5 valence electrons,
-2.
minus 1, 2, 3. That means its
5.
formal charge is 2, minus 1/2 of 2. Then there are 4 total. 1/2 of 4 is 2.
Right.
So 2, 3, 4, 5, 5 minus 5, its formal charge is 0. Okay. But you still got to figure out the rules and all of that associated to why a better formal charge structure is going to match over what makes a better formal charge structure and whatever else. So go back through the notes on that. Okay. Okay, moving forward. So these are called free radicals. They tend to be extremely unstable. They react with everything. They react with nucleic acids. They react with proteins, amino acids, everything else. So in a biological structure, it's a big problem. There are a lot of things that scavenger in your cells to prevent that or to house it, right? And you learn that when you get to biochemistry. But things like copper zinc superoxide dismutase will move through. And what they basically have is they have, in that case, copper and zinc are 2 transition metals that could absorb that electron density and move it and distribute it around different d orbitals to house it or to prevent it from interacting with other things. So those big enzymes that scavenger the free radicals generally have some transition metals that are able to move it back and forth and shield other things from that electron and the activity of that electron.
Is that what they try to also contain in a nuclear plant? Like the free radicals, they try to emphasize the safety of it? Is that what they're
Not
coming
sure.
from or no?
I'm not sure in the context you're referencing it. So in terms of nuclear chemistry, it might have a role, but I'm not sure in the context how you just described it. Maybe, I just don't know.
Okay.
Okay, so what I have here, NO reacts with oxygen, you form NO2. So NO plus O2 gives you this NO2. And you can see these 2 different structures. What are these called?
Oh, I see.
Resonance structures, right? And how do I know that if I wasn't sure? I got the double arrow here. What's this structure really look like? A hybrid, right? We talked about that. It's more of a hybrid. Why is it more of a hybrid? How do I know that? But how do I know it's not a bunch of these and not just a hybrid between these, where the electron density of this one and this one is shared between both positions?
Because there's that double bond there, so does that make
I discussed this on Tuesday. The length of this bond versus the length of that, what would you expect? The single be longer or shorter than the double?
Oh, longer.
Longer.
Right.
Okay. Single is longer than the double, right? Because you have 4 electrons here, only 2 here, so that's wider, that's shorter.
Correct.
Okay. That means that if I looked at the distance in picometers between this and this, I should have 50-50 if I have both structures. But instead, I find more of a hybrid between the 2 in terms of its length, so I know that it's more shared. And that makes more sense anyways, because if the electrons are localized here and localized here, then only those 2 areas are absorbing the electron density. If it's distributed throughout both, then I delocalize that electron density, and that creates a more stable compound. Right, and that's something we talked about Tuesday. Okay. And by the way, you notice the dot there, that means that if I go through the formal charges, the formal charges are going to favor having the dot on the nitrogen than on the oxygen.
Maybe 2,
Right.
3, 4, so it's 1.
What do you mean it's gonna favor?
It's gonna be the one.
You're going to have a
charge.
greater overall formal charge if I move the dot from the nitrogen to make it on the oxygen and pair up the nitrogen.
Right.
The formal charges will be greater if I move it to one of the oxygens. That's what I'm saying.
The oxygen would be negative.
The overall formal charge.
Mhm.
Okay. So that's the first one. Next one, incomplete octet. So when I say incomplete, I don't remember if I've spoken about this before in any class prior, but when I look over here, what would I expect is an incomplete one? Where might I start assessing which positions here? And remember, I'm looking at a let me rephrase this. Let me make sure this is in the proper context. I'm looking at a compound where something is the center atom. That center atom does not have a complete octet. That means incomplete means it has less than an octet.
Right.
Now, with that knowledge, looking at this here, where might I find that? Where? Fluorine. Now, why fluorine? Would fluorine ever be a center atom first?
Or not
No.
the center atom, but like.
So let me go back. I'm looking at a compound, and I'm looking at the center atom not having a complete octet. That means it has less than 8 electrons around it. Not an odd number, that's what we just covered, but less. So 6, 4, 2, those would be incomplete as examples.
Okay.
What am I more likely to have and why?
As the incomplete will be the carbon?
The what?
Carbon? Oh, the nitrogen?
Carbon would form how many bonds always? Why? Lewis symbols shows the 4 electrons, 1 in each position for bonding.
Correct.
You're kind of on the right track though, okay? So putting that in context, what are you referencing? You're referencing shared electrons.
Right.
So where would I be sharing electrons where I would not have that complete octet? Covalent bonding, yes. And what element? You were really close on your carbon.
Nitrogen.
What about boron?
Oh,
I heard that back there, right?
5. You got
What about
5.
beryllium?
1, 2, 3, 4.
Do they have electrons in the D shell there, at the ground state? No, because it only goes to the second level. So that means I have 1s, 2s, 2p. In the 2p for beryllium, do I have anything there? No. In the 2s, do I have anything?
Right.
Complete shell there, right?
Correct.
What about the boron? How does that one work?
It will be 1 more.
I have 3 electrons, right?
Correct. One in the outer.
What if I put boron in a compound with fluorine? Would it be a covalent bond or would it be an ionic bond?
It's
Covalent?
right. Polar.
So it's
covalent?
going to form how many bonds with those 3 electrons? 3 bonds, which gives you 6 electrons around it, absolutely. Beryllium, if it was in a compound, it has only 2 electrons. Presumably, if it's in an ionic bond, what would it do? Lose the 2 and form a 2+?
Mhm.
It's in group 2. What if it was in a different compound? What if it was in a covalent compound? It'd form how many bonds?
1.
How many valence electrons? 2. Potentially form 2 bonds. So those would be 2 center atoms that would have incomplete octets. Now, if I go beyond that, I get into the 3rd period. Would I have anything there that potentially does that? Why would I or wouldn't I have anything that does that there? What makes the 3rd period different than the 2nd period?
It already has an octet.
The d orbitals.
Extra, right.
You have d orbitals. So that changes things a little bit. I don't have any d orbitals in the other one.
You don't have any orbitals in period 3 either.
3, but not 2. That's what I'm talking
3D,
about.
right.
3D.
Right.
Yes, I know what you're talking about.
You just lowered
Right.
in the periodic table, right? Yeah.
So that means I have availability for interactions in those. But I don't in the 2nd level, where I have beryllium and boron. Okay, so, oh, did I click this too fast? So here, I have boron, for example, and boron can make 3 connections, hydrogen or fluorine, and covalently bound. And you can see that it's only going to form 3. It doesn't have the extra 2 for the 8 because it doesn't have an extra electron to share. and it's stable in just that type of conformation, whether it's BF3, BH3, or whatever else. So that would be an example of a stable, incomplete octet around the center atom of a compound. Boron, beryllium would be another one. But those would be the only two because they don't have the d orbitals. Okay.
We're just making it six
Now,
electrons.
If you look here, okay, so another way to assess this, so for example, why do we know that this is stable? Why can't I do something like pull down if I look here, why can't I take one of these? So in this case here, I have extra electrons around these. Why can't I take these and pull down and make a double bond so that my boron has a complete octet?
It's not the ones supposed to have one and one electron.
Well, so the whole reason we talked on Tuesday about formal charges and the structures, we're almost always going to rely on that to determine whether or not it would be more stable or not by doing that.
But then the affinity of.
So if I go here, like so, for example, here, what I'm saying is I could make this one or this one or this one a double bond, and now I have my complete octet around my center atom there. So why wouldn't I do that, is the question. Right, that would solve our issue with the Lewis structure in terms of the octet. But if I do that, then and I check and I look at the formal charges, what do I see? I see a -1 and a +1. I know that that's bad in all kinds of ways, right? Why is that bad? In other words, the +1 and -1 on their own are not that big of a deal, right? Unless I can get a 0 and a 0 formal charge.
Yeah.
Then I have a better structure. But overall, that's not like it's not like a +2 and a -2 wherever. But where are they located on? The fluorine now has a what? +1. Fluorine is the most electron negative element. So why would it ever want to form a positive charge?
Never.
Wouldn't.
Right.
That would create something that would not function well here.
0 is fine, yeah, right.
See that? Does that make sense? So if this had maybe been a +1 here and a -1 there,
Then it might have worked.
then maybe it would be stable enough to work in nature. But because of this, it doesn't matter which one I do, right? All the fluorines are presumably chemically similar or the same or equivalent. So I'm not worried about that. So if I put this into the compound and I say, okay, what are my formal charges? I can quickly see not only do I have a greater formal charge on the overall structure from the other one, which would be 0, 0, 0, but I also have the negative on the wrong atom, which would create a lot of instability, making the charge, even though it's only a +1 and a -1, even more magnified to why this would be an unstable compound.
But why would it be more unstable versus the other option that you said if the other fluorine would have been -1 and the one of them was +1?
Wait, go back. What
You
did
said
say?
you said if the other fluorine was instead of 0,
No,
it
I
would
said
be
if this
-1.
one, not the, when you say another one, I don't know what you mean by that. I'm saying they're all the same, no matter which one I do, but if this became a -1, this is a +1, that then would be a little more stable
Oh,
than the way
okay.
it's orientated now.
I thought you said it was the other fluorine being -1.
Doesn't
the
matter
one on
which
the right.
fluorine I use.
I mean, keeping that one positive, and then the
Well,
other.
it wouldn't unless I made 2 double bonds,
Gotcha.
right?
Oh yeah.
Then I have now a greater number of electrons around the center atom, not less.
Correct.
Right.
I just still don't understand why boron's like okay with having 6 valence electrons. So it's the formal charge, right? But, like,
How are we assessing formal charge, and what does the formal charge mean?
So ideally they want to be 0, right?
Okay.
Right.
So then what's the challenge there in concept?
So
What are you challenged with on that? Why is that an issue for
So
you?
fluorine got 4. 1, 2, 3, 2, 3, 4. Oh yeah, it's 0. Huh. Boron will be 0.
What's the challenge?
Well, in this case, it's going to be +1.
Boron has 3 valence electrons.
Oh, 3. Yeah.
1, 2, 3. It now has a formal charge of 0.
Right.
Fluorine has 7, -6, -1, 0. And of course, if that one, these are all the same. That's a more stable compound than that, just on its own.
Mm-hmm.
Oh, I see. Okay. And then, so
But what magnifies this being bad is that the negative shows up on the boron, not the fluorine. That makes it even worse. Not only is it not a good fit compared to this on formal charges, it's also reversed where the charges should be if you were going to have formal charges. Because fluorine is the most electron negative. Therefore, it should be the one absorbing the negative charge. So if it's not absorbing the negative charge, and this one is, and it's now absorbing a positive charge, you've now created a greater
Stability, right? Unstable.
issue with the compound being together, meaning that I now have more energy needed to hold that together as a result.
Correct.
And that's why you would not find it naturally.
So what'd you say the other one that would have that too is aluminum, right?
No, beryllium as a 2+.
Oh, okay.
So beryllium and boron would be the two that form incomplete octets. And the rationale would be because of the formal charge distribution. And also the type of formal charge that you would get on each individual atom as a result of that formal charge.
So like boron chloride?
What's that?
Like boron and chloride?
That would also, yeah,
Okay.
right? Any of those,
Group 7.
boron and hydrogen.
Anyone group 7?
Why else though? Okay, so what other possibility could I have here? What if I said, why not have BF4?
That would
Would that work?
Then that boron would have a
boron.
negative, or boron would have a negative.
I put another F here. I'm taking one from the fluorine and I now don't have a complete. So I'd have to take two here and then I'd have what? An odd charge on an odd number of electrons on the terminal atom in terms of fluorine. What about hydrogen? It only comes in with one. What's it bonding to? Nothing. Can't form a bond. So that's why it doesn't form all four. That's what I mentioned originally where it has three positions to form. And then based on formal charges will dictate why you do not have double bonds or anything else associated with it. And it's the most stable in that conformation, which is really all we're looking at is what is the most stable and therefore what's naturally found. And if it's an anomaly or something different, then this is some of the rationale to why that is. That's only going to happen on level 2 with beryllium and boron, for the most part. It's not forced, at least, or something that's in its most stable. Now, that does not mean that I can't take something like ammonia. So this is ammonia here, right? NH3. And that has two lone pairs, or one lone pair, 2 electrons sitting on top of it. I could take these two and bind to the boron, forming a bigger complex, but there I have 2 electrons to share with it.
Correct.
In fact, that's called electron donating. And in that context, when electrons are being donated, you could think of that as a type of acid or base, right? That's called a Lewis base. And now that makes the other thing a Lewis acid, which is something you'll learn in 102. And this thing then would change whether or not you're just looking at hydrogens in terms of whether or not it's acid, or just hydroxides in terms of whether something's a base. This is another way to define acid and base relationships.
So the Bronston-Lowry one was.
That's not a Bronston-Lowry.
No,
Lewis.
I'm trying to decipher the two. So
Different.
Yeah, I know. So
Proton
Bronston-Lowry's
donor,
were-
proton acceptor.
Okay. Yeah.
This is electron donor, electron acceptor.
Okay.
Is that what you're looking for?
Yeah.
Proton versus electrons. Proton is just H+, right? That's a, what did you call it?
Bronston-Lowry.
Bronston-Lowry. Arrhenius is what? What was Arrhenius's?
I don't remember that one.
The other one that's left, neutrons?
In solution, you form either H+, or hydronium ion, or hydroxide ion. That's Arrhenius, right? So this would be, you'll learn that this is also considered a base. It's just called a Lewis acid or Lewis base connection. And we'll talk more about that in 102. But so this can make a connection if you have 2 available electrons to bind to it. Okay, and that will be considered, as you'll see, an acid-base pair in terms of Lewis acid, Lewis base is a completely new way to define an acid or base because of what it does to the solution and the surrounding water as a result. Okay. Expanded octets, that means I have what?
More than
More than
more than 8 electrons around it or more than 4 bonds. Okay. So once again, so at that point, the odd number was just 1. Then we had the deficient one, that was only on level 2. Now we're looking at something that has more, it has to be on level 3, where you do have the d orbital space to connect to. Okay. And now you'll see sometimes up to 12 or 14 electrons around it. Keep this one in mind, because this one's going to play a role when we get into chapter 10, because you're going to have bigger structures, bigger three-dimensional structures as a result of this one. Right? So the 3, no big deal. You already know the VSEPR structure of something 3, trigonal planar, stuff like that, right? Something 2, beryllium, linear. But now what you don't know, and we're going to learn through VSEPR, is you'll now get bigger parent structures if you have more than 8 electrons around the center atom. Right? In this case, I'm looking at, you get 10, 12, 14, whatever, and they're usually somewhere around, obviously they have to be past the 3rd level up here, but they're usually somewhere around here. So you're looking at phosphorus, sulfur, and some of those things. You've actually been exposed to that. So I think we did some experiments at 65, maybe 101, where we said, what were they? I think they might have been synthesis reactions, where we looked at phosphorus binding to oxygen, and you ended up with P4O10. And then we just said the P4 came from just 4 individual phosphates, and then sometimes people would put P4.
Oh, that was one of the lab questions.
Right, yes. It was P4 versus 4 Ps.
Right.
Right? So this is them all being bound together. You get a bigger structure. Sometimes you see S8 and some of those kinds of things. That's because of this, the expanded octet around the center. They're able to house other electrons in their d orbitals that create a stability that's okay with the system based on formal charge structures. And so here you see SF6. That means it has 6 fluorines binding to 1 S, 1 sulfur. So what would be the 3-dimensional structure of that? Let me rephrase. If this was SF4, what would be the 3-dimensional structure? Tetrahedral, right? Tetrahedral. If it's F6, what is it? What if it's F5?
A penta.
Have we seen that? No. That's what we're going to explore in chapter 10. That's the extension from what we already know from what we learned here in 65, or at least what we learned in 65, right?
65, right.
So that's what chapter 10 is going to talk about. So that's why I want you to take note of what we're doing in the expanded octets, because this is going to come back up when we talk about structures. Okay, like a bipyramidal is going to be SF5, SF6, octahedral.
Oh.
And that will have a different structure. Okay, that makes sense? So some of these can house those and create more stable structures, 3-dimensional structures, as a result of having more than octets around the center atom.
Okay.
Okay.
What we saw was the.
There's 5. Here's some examples of that. If I was just going to draw it out, Lewis structure, I have 1, 2, 3, 4, and then I have 6 here. And basically what I have now, these 3 are going to be in the center going around it. These 2 are going to be up and down. So these are going to be considered equatorial.
Okay.
And the other 2 are going to be considered axial. And we'll explore that in chapter 10. Same thing here, except for here I'm going to have 4 equatorial. These 4 are going to sit like this and go around it. And the other 2 are going to have 1 up, 1 down. So you can see the bond angles here are going to be just 90, 90, 90, 90. Here, the bond angles between the equatorial are going to be 90, but the ones in between here are going to be 120, 120, 120.
Okay, so it's always going to be 1 on top.
So they're going to be different.
Okay.
That's going to be the trigonal bipyramidal. This is going to be the octahedral.
Can it be more going like on the top like this? No. It has to go
You
straight.
can, but this is as far as we're going to get. And what happens when these are just the parents, what if I pluck one off? Which one do I pluck off first?
Okay.
What does the whole structure become? You're going to see different structures. So I don't know if you recall, but in 65, I think I talked about anything that's a derivative from the parent
Right.
is going to be polar. Now I could potentially, from these structures as parent, I could create derivatives that now are non-polar. Okay.
Okay,
As an
yeah.
example, what if I took off all 3 equatorial positions? Now everywhere around the molecule is the same.
Right.
It's non-polar as a derivative.
Equal, yeah.
Okay. And then we get other things like we're going to get a seesaw shape and some other things. We'll talk about that in the next chapter, either later today or Tuesday, we'll be talking about this. So I kind of want to introduce it now and how this plays a role and is relevant later on. Okay. 10 around this one, 12 around this one.
Mhm.
So once again, because they have d orbitals.
Expanded
um,
optics.
Okay. So that's really all I need you to know about the expanded and about the different ones.
Only in period 3?
The above period 3 and above,
Okay.
where you have these. So if I look here, I could always go to the formal structures, right? And I say, what is this here? And you can see the charges. What else do I have here? Okay. So at some level, you can say, okay, but what is this?
As for
Is this an acid first? Oxyacid?
oh yeah,
Yes, hydrogen's connected to the oxygen.
yeah.
What do I have for oxyacids? What's the core of those usually? Polyatomic ion, connected with the hydrogens, which are connected to the oxygens, making them oxyacids. So what is this? Sulfuric acid, right?
Yeah, so for
That should be very quick, right? H2SO4, if I put it in terms of a structure, of a formula.
Yeah, right.
All of a sudden now it makes sense.
Yeah.
I'm expanding these things. You guys are now learning the actual structures of them as opposed to just the formulas. Okay? Okay. If I were to draw out the Lewis structure of that, how would I do it? Forget this is on the board.
Mhm.
How many valence electrons does this system have? I have 6
6,
times 4 is 24, 25, 26, and that's what? Right there. Another 6. So I have 6 times 5,
6 times 5, is that 30?
30 plus 2, 32.
32, right.
Then I move them around the same way I plug them in. I know the hydrogens are connected to the oxygen. That's why they're oxoacids, right? That's why it's sulfuric acid. And I end up with 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That's the structure. In fact, didn't I do this for you when we did, didn't we do this on Tuesday? Didn't I show you phosphate on the sideboard because it wasn't on the screen? I did a Lewis structure of phosphate.
Yeah.
He was in the
And
center.
you remember where I said that this is not probably how it is, but this is how the proper Lewis structure was.
Yeah,
Yeah.
Maybe it forms double bonds, and then somebody said, what do you mean? And I said, we'll get to that.
yeah. Mona.
Now we're getting to
I
it.
was going to decide.
Right? Does this make sense? It's starting to correlate what I was talking about. So here, you can see in the formal charges, it's not terrible, but it's not great. Plus 2, minus 1. Notice the minus 1s are on the proper atom here. They're on what? The more electron negative one?
Mhm.
Is oxygen more electron negative than sulfur?
Yeah.
Okay, so this is a semi-acceptable, unlike what we saw with boron when I double bonded the fluorine. Right,
Yeah.
the fluorine took the positive charge. That's a real bad thing.
2.58 versus 3.44.
But now I have the sulfur with the positive and the oxygens with the negative, so I'm okay there. But I still have some formal charges. Can I develop a structure that still fits the Lewis structure scheme and reduce the formal charges? And that's what I'm going to look into next. Okay. So if I do something like this, where I double bond here and here, look what happens to the formal charges.
Look at that, 0 gone.
I just created a
Zero,
better
zero.
formal charge structure. By doing that, I've now relieved some stress within the structure and therefore reduced the amount of energy it takes to hold it all together.
Would that be a hybrid, those double bonds then, right there, between those two oxides? Or no?
Say that again?
Like, how we looked at, like, naturally, like, would that be, like a hybrid or no? Like, what's,
You mean, would they be resonance structures?
yeah,
So I'm gonna just entertain this for others because that might be a point of confusion. Okay, so let's look at this.
Did it could go either way? No.
Versus
Oh.
this.
oh, I see.
Why don't I-
What's different between those? What's different between that and these two? Forget about what's connected here because I'm not worried
There's
about
two
that.
bonds there.
Yes. Okay? Okay. So clearly, we're not looking at resonance here.
Correct.
That's important, though, for make sure that's clear. They already have the double bonds in both positions here. Okay. So this, as I said, now creates a more stable complex. As a result of that, it takes less energy to hold it all together, and therefore it's more likely to find this in nature than the other one. Simply determined by formal charges, because the formal charges are going to represent the stress or lack of stress and tension within the molecule itself and how things are bound to it, based on charges and likeness of wanting electron density towards it or not relative to the nucleus of each individual atom, and then how they interact with each other. Okay. Okay, okay, that's all great in theory. Okay? The theory there, sound, solid, makes sense. Is it real? And the argument is yes, because experiments have been done, and what in the other structure, these would be single bonds, right? Everybody agree with that?
Correct.
So these are the same, so it would just be this structure here. And what you actually find, then you would expect the bond lengths to all be single. And what you find is more often you find the double bonds, because the lengths are different. They're smaller, shorter. So that means experimentally, not only does this fit intellectually, it fits experimentally over this. So that's the confirmation that the idea matches reality. Okay. Okay, so test question. Which molecule could have the expanded octet out of these three? Which one? I heard some. Trade. You said A. Anybody agree or disagree?
Expanded octet. B.
B. Why?
We have the 4 oxygens, so we got around the P and then the 3 of the. Oh, wait a minute. With the P in the center, yeah.
As only a quick announcement regarding tutoring, if I'm able to.
Right in the middle of the lecture.
I know.
Terrible time, right?
I was just waiting here.
Go ahead.
Just real quick, next week, Monday to Thursday, we're extending our hours in tutoring up till 10 p.m. so you can serve for finals, and we have free pizza. That's all. Sorry about that.
How much is the pizza?
Free. Till 10 p.m. next week. Just next week only.
Thank
Thank you.
Sorry about that.
So maybe I'll come with you.
I'll bring you some.
So what's the rationale here? There's got to be a reason for this. There's clearly one over the other, and it's going to be embedded in this information that I've given you up to now.
Yeah, the O's connects evenly into the P.
They all
in
have
the
O's,
center.
they all have center atoms. What's the center atom on all of them? They're all acids. The center atom, nitrogen, phosphorus, carbon.
Right.
They all have oxygens, they all have hydrogens. What's the difference between those? Let's start with that. If you don't know anything else, what would you start with?
The balance
Of the things I just mentioned, what are the differences between them?
Oh, the amount of oxygen.
The center atoms are different.
Okay, good, right. But
It's
also the amount.
glaringly obvious that, right? They all have oxygens, they all have hydrogen. The center atom is different.
Right.
How does the difference in the center atom matter to whether or not I can have an expanded octet?
It would only be between B and C.
Oh, it has to
On
be
that.
the 3P.
Yes!
The third period.
That should be blatantly obvious.
So it'd be
What is carbon and nitrogen? What level are they on the periodic table?
So,
there on the
2. So do they have the third
no. It's on 3 only.
level? No. Remember what was one of the criteria for the expanded? They have to be on the third level or beyond. It's a very, kind of like the exams, right? Some of these concepts, I'm not asking that much out of it.
And I asked
You just
you.
have, yes.
I asked only 3, not
Yes.
beyond. Okay, good.
These are things that I'm explaining, and all you got to do is follow those basic things and just think about it conceptually, and it's pretty obvious. Unless I'm way off, it should be B for that reason. Right? And it didn't take that much thought, and on an exam that should have taken you a whole 5 seconds, 4 seconds, something like that, and you could move on.
Yeah.
Somebody want to help?
It's on period 3 and after? Anything on that?
'cause it doesn't
Nitrogen
have
is on
the-
period 2.
The 3D orbital to mess with it. Because the D, it goes downward in energy level, so that's 3D. So it messes with anything on the third period and on. So the only one ones that can have an expanded octet is if they're on the 3rd period or below.
Because what is first of all, what does expanded octet mean?
It can make more than 4.
It can make more than 8 electrons around it.
Which is maximum
Okay,
10.
so that means where are they going? When you look at the valence electrons, when you talk about octets, where are they?
They're going to
Maybe I should break this down a little bit more.
3D, the D.
The P's
Mhm.
and the S. 1s, 3 P's,
Mhm.
4 orbitals that create enough to house 8 electrons.
Yes.
That's your octet. Okay, maybe I should have explained that. That's implicit, I think, at this level, but maybe not. So if I'm going to add electrons to that center atom, where else can they go?
The D.
Potentially in the D.
Mhm.
So I have to be on level 3 or below in order to get those, gain access to those D orbitals. And now if I fit more connections of electrons into those D orbitals, I now can create something that's called what we're calling an expanded octet.
Is it important to know where they go versus
The specific one, no.
Like the F or the D, and that point, could it matter on
D,
that?
you're always gonna go D next.
Okay.
We haven't got anywhere near F and will not at this level. You don't have to worry about F. Is that okay? Oh,
Yeah.
make sense?
Yeah.
Okay, so breaking it down and understanding the concept of where each thing was, and then that just be pretty straightforward. If I didn't know anything else, let's say I'm on a test taking skills, right? I'm on an exam and I'm looking at this. I could say CPDN, just like I said, I would have identified that quickly as those are the different things in each compound. Then I would have gone to the periodic table and said, CNP. The C and the N are on the 2nd level. Maybe it has something to do with that. So your P's on a different level. So even if I didn't know anything, I could have done that. And that could have led me to the answer. Right? What am I doing? I got to identify differences because clearly one is different than the other two. What is that difference?
Yeah, yeah.
And if I look at the center atom, I could see that they're on different levels if I look at them on the periodic table. And then at that point, then I say I could make up something close, and you're going to get partial credit, right? Because you actually are right, even if it's not the exact reason. They'll give you some credit for it, just for identifying that difference.
So if you go down the periodic table.
Yeah, then you could have expanded octets. Yes, absolutely. Not if you go up, but if you go down, yes. Doesn't mean you will. Then you have to start looking at formal charges and things. This question just simply asks which molecule could have. I didn't ask which one does have, what it looks like, where they are. I didn't ask anything specific. All I said is which molecule could have an expanded octet. It's not a complicated question. It's not in depth in any way at all. It's just an understanding of where you could have an expanded octet. That's it. Is that okay? That's essentially what these questions are on the exam if you think about it. None of them go that deep. I may go deeper just for help for intellectual understanding for you guys in here, but the questions generally don't go that deep.
The amount of oxygen would never matter?
Not in this case.
Okay,
Unless there's only one versus multiple.
correct.
If the hydrogen isn't connected to the oxygen, that would matter,
Okay.
right? So there could be some differences, but all of these are designed in a way just to look at that one piece of information and make that determination.
Okay.
Okay. Write the Lewis structure for XEF2. Okay, so let's do that. We're running out of time, so let's just go 22 electrons. I form something like this.
Right.
What did I get? I got an expanded octet, essentially,
Yeah.
right? Or expanded Lewis center atom in terms of its electrons.
Right.
I have 22. I fill in the outer. By the way, let me do this real quick. This is something you would have done on the lab thing if we were doing the lab for this one. So 22, my center atom is Xe, FF, bond, 22 minus 4, 2, 4, gives me 18. Maybe I should do this where I have more space. 22 minus 4 is 18. 2, 4, 6, 8, 10, 12, minus 12. What do I have left? 6. Okay. In the past, sometimes you don't have enough to make the octet on the center atom, right? In this case, I have 6, so I go 2, 2, minus 2. I still have 2 left. Okay, what do? Xe, where is Xe?
It's a noble gas.
It's a noble gas, and got
Period five.
definitely our third energy level, whatever.
Mhm.
Okay, so the only place, is it gonna go on a fluorine?
No.
No. Is it gonna go here? Potentially, so I look at the center atom, I add the extra 2 there, and now I have an
You can put it in
expanded
the bottom.
octet here. In fact, xenon does form something like this with only a couple different,
You put it on the bottom.
couple different things. I think I also
But not
did,
on the sides.
we did a
It's
problem
the
like
period
this
on
at some point in one of the lectures, I don't recall now.
Is there a blatant reason why xenon has 3, like, electron,
Um,
they're called,
lone
bonded
pairs?
as opposed to having a double bond with fluorine?
Lone pair?
Is there
Well,
any
yeah, I
particular
mean,
reason,
this-
or
yeah,
just
absolutely, watch.
put it through?
How many electrons are
Oh,
on the
'cause
fluorine
the
now?
fluorine
Yeah.
is-
Yeah, yeah, so for that, yeah.
That makes it a negative charge?
So you can now see that if you were drawing this and you had extra electrons, you're just going to put them around the center atom as expected, and that's how you make it. And of course, if I do the formal charges here, Xe is what, 8 minus 2, 4, 6. That would be 2 left, 1, 2.
Right.
So its formal charge is 0. So actually the formal charges work out. Same for the fluorines, everything is 0, 0, 0. So if I look at that from a formal charge perspective, I also have a perfect formal charge structure.
Gotcha.
So that means it does have a level of stability with the expanded octet. Go ahead.
If you did have a formal charge distribution, you would give it to the fluorine, right?
No, 2 things. One is no, because the fluorine doesn't really like to absorb that much electron density once it's already stable. 2 is why would you not want it to have formal charge?
Well,
In other words, why would you create a scenario that doesn't exist? Formal charge is relevant, so why admit it in any context?
we're just saying like if you do get yourself in a situation like the boron one, where fluorine had the positive 2 elements,
Mm-hmm.
you said that would be impossible because if you wanted to have a charge, it would be negative, right? Because
The fluorine would be a negative formal charge, which is different than having an expanded octet around the fluorine. Those are 2 different things, right? Do you see what I'm saying? You're saying if I created a formal charge around the fluorine by enhancing the octet, you don't have to enhance the octet in order to have a different formal charge. Watch.
Yeah, boron is actually forming a negative.
Fluorine connected to whatever here
Mm-hmm.
versus fluorine
That's 4, 6, 8.
connected with a single bond.
That's 4, 6.
They both have 7 valence electrons.
Right.
This is 7 minus 6 minus 1, this formal charge is 0.
Mm-hmm.
This is 7 minus 4 is 3 minus 2
Mhm.
is 1. That's a plus 1. I didn't change the number of, I didn't change the octet, but I did change the formal charge of it.
Hmm?
I don't have to do an expanded octet to have a change in charge. Is that okay? Okay.
The electronegativity?
Okay.
Would have
So,
on the outside. He wants to.
let me take a look, what do we have here? ClO2. Cl, for some reason, likes to do a variety of different things. It's also on, by the way, fluorine is also not going to have an expanded octet. Why? I should just clarify this, just as the base. It's on the second level.
Mhm.
So it's not ever going to have that expanded octet. Doesn't mean it can't have a change in formal charge, but it's never going to have an expanded octet.
formal charge is the one.
Formal charge is the one that's going to, yeah, that's what you put together to dictate. You got to read that. That's what we covered on Tuesday. You missed Tuesday, huh?
Yeah.
Cover that. That's important material, and that's really relevant to the exam. The final. Make sure you go over it.
Which one?
Formal charge. You were here.
Yeah.
Okay, so what's the center atom here?
CL?
Cl. O's on the side. I have 7 plus 2 and 2,
So
19. Ooh, what do I have here?
odd, it's gonna be a.
It's going to be an odd one, yes, absolutely. Okay, so let's do this here, and the negative of the extra electron in this case is right here.
Yeah.
And the, just double checking, the extra electron goes on the center atom,
Right.
Usually.
usually.
But
not
remember,
always.
there was one where it wasn't one wasn't centered, just 2 atoms, there was no
Yeah.
center. So in that case, you had to determine formal charge.
Okay.
Set up the formal charge. Formal charge on the oxygens,
0?
0?
Yeah, 0.
Okay, or is it -1 here? So I have 6 minus 6
minus
is 0, minus
two.
1, I have -1, -1. Over here I have 7 minus 1,
6.
minus 2, so minus 7 minus 3 is 4, minus 2 I end up with a plus 2. So this formal charge structure is not that stable. But then again, no odd electron one is going to be stable. That's not a good structure. Oh, there it is. Probably, but what if I change it? What did I do there? I formed the double bond. What did that do to the formal charges?
Oh, zeros. For the oxygens, yeah.
Change
And
to
everything.
0, I just created a what? More
Unstable.
stable,
Mhm.
odd number electron compound.
That's formal charge. Plays in a role.
Does everybody see that? Go ahead.
Just to be clear,
It's like
the
coffee.
extra electron, doesn't matter where it goes, like either the top.
No,
or
it does
bottom?
matter. If,
No.
oh, you mean, no, no, no.
The long
Just
thing.
as
Not
long
at
as
all.
it's on the middle. Okay.
Absolutely. Top, bottom makes no difference. Orientation of it. Go ahead.
In the test, does it matter which way you put it, if you want it?
What do you mean?
Top to
So
top?
Let's say it says write the Lewis structure for the molecules, and you go to the one with the unstable one?
This one?
Yeah.
That's wrong.
Yeah,
Right.
that one.
Yes, that's right. In nature, you won't find this over this.
Mhm.
That's exactly the point. So in nature, you'd find this. Intellectually, because it has a lower formal charge. Experimentally, because you're going to see double bonds between the O and the C, not single bonds. And that verifies that this is the way it is, how we define it intellectually. So all it says is that our ideas and how these things work can, at least it sometimes can be shown experimentally. What about this one?
Beryllium in the middle?
Beryllium in the middle, another 2 bonds.
Beryllium in the middle, chlorine's on the outside, okay?
Wouldn't
16 electrons, so I form this.
It would inform the other.
What are the formal charges on this? What is the, okay. Let me make this clear. What am I doing in all of these that's a deviation from what you learned in 65 or the equivalent?
Using formal charges to check
Yeah.
how stable it is.
Absolutely.
Mhm.
In the past, you never worried about formal charges or these odd situations.
Correct.
Now you're putting together things and you're going to care. What are you going to do? You're going to look at the formal charges and make the determination as a result of that. And you're going to make adjustments to the Lewis structure as a result of that. And what does that do overall, even though we haven't got there yet?
Lower the energy.
It makes the
difference.
structure different.
Right.
If it's got a different structure, especially biologically, does that matter? Yes. The structure of things dominate and determine their function.
Right.
Their function are what makes us move and operate appropriately, whether it's at the cellular level or beyond.
Right.
So the function matters a lot, and the structure dictates that function. So by identifying what the structures look like, help us understand what the functions are. Okay?
Well, all charges are 0 in this one.
So this one, so what are the formal charges on this one?
0,
Whoops.
0, 0.
7 minus 6 minus 7, 0. What is this? 2
Two.
minus 2, 0. 7 minus 7, 0.
Right.
That's a good structure. It's stable. I don't have to go. It's different, not expected.
Yeah.
It doesn't have the octet around the beryllium, but it's stable. So I'm okay.
It wouldn't be able to form the above the octet.
If I turn these in, what happens to the formal charge?
It would, yeah, it would
Goes
be-
up.
Right.
Formal charge goes up. What does that do to the compound? It makes it less stable,
Right.
more tension between the atoms. As I get more tension between the atoms, less stable, that means it takes more energy to hold it together. And if I'm a molecule in nature, I want to be more stable, I want less energy, I'm going to go with the less energetic structure. Okay, we're going to transition now to finish off this chapter. Hopefully we can finish this with bond energy and bond length. Okay, and let's start with bond energy, and then we're going to look at how those things correlate with each other. Okay, so bond energy is essentially break 1 mole of a bond of something in the gas phase. That's it. I look at something in the gas phase. How much energy does it take to break that bond? Okay. I look at Cl and Cl bond from Cl2, and I see it takes 243 kilojoules per mole to break that. Bond energy is always energy put into the system used to break the bond. It costs me energy to do that. Let's establish that now. When two things come together, I gain energy from that. What was that called?
Latisse.
Latisse. See
Oh,
how
latisse,
easy it is for
right,
me to
latisse.
get that out of you? I just say la, and everything, latisse, yeah,
Latisse
yeah.
energy.
Before that, though, it's like tongue-tied. You need to know these things. So when I put two things together, I get energy out.
Mm-hmm.
When I take two things and I break them, I have to put energy in to break it.
Correct.
If I take two things that are stable, it takes me more energy to break it. If I put together two things if I break a stable bond and create a weak bond, overall that's going to cost me energy. That should make sense. It'd take me a lot of energy to separate it and very little to put it together.
Yeah.
If
More
I take
entropy.
something that's a weak bond and break it, it took me less energy to do that. I then put together two other things and it's a strong bond, then I get a lot of energy out of that, then that's going to be something that's favorable. I'm going to get energy back from that.
Lower in entropy?
My delta H will be negative
Lower, right.
or exothermic.
Mm-hmm.
How would that like play a role with entropy?
We haven't even introduced entropy in this class, right?
No.
Enthalpy or entropy?
Mm-hmm.
Entropy is the disorder.
Correct.
That's looking for something relative to its spontaneity.
Surroundings?
We're talking here about enthalpy. Overall energy needed to break old bonds, make new bonds.
Correct.
Enthalpy does not have to be spontaneous, which means it does not have to have a positive entropy, which also means it does not necessarily have free energy gained, which would normally be called Gibbs free energy.
Gibbs,
That we haven't even touched on, and we won't get to that till the end of 102 next semester. We've only talked in terms of our thermochemistry in this class of enthalpy,
Okay.
not entropy, not yet. Okay.
Gonna help in biology?
Yeah. So the thing here is now, I'm looking at breaking bonds, making new bonds. Takes energy to break them, I get energy back making them. Okay? If I have a single bond, it's easier to break than a double bond, which is easier to break than a triple bond. That should be intuitive. The longer the bond is, the easier it is to break. When I say easier, it means it takes less energy to do that. That's all I'm saying. So I look here, and I get this amount of enthalpy. So that's a positive number. That means it went in to break it, right? If you remember delta H's. Over here, breaking the CCl bond, the ClCl bond versus the HCl bond, it actually takes more energy to break the HCl bond than the ClCl bond. What can I take home from that information?
So ionic? Any ionic bond? Easier?
If it took more energy to break it, what does that mean?
Stronger.
It's more stable.
Right.
This is a stronger bond. That's all you have to interpret here. That simple. Bond energy is always positive because it takes energy, nothing that I haven't already said, but I better re-emphasize that. So I notice that sometimes I say things and then this goes right over, right? Like third period over there. I'm going to make sure that I say things enough times to get it through. Okay. More stable, blah, blah, blah. N2, breaking an N2 bond takes a lot of energy, which means it's really stable. Why is that? It's what?
Well, Cl is diatomic too. That was pretty easy to break.
The triple bond?
What is it?
The triple bond?
Ah, it's a triple bond. Remember, nitrogen's a triple bond.
Right.
Oh, so.
Chlorine and chlorine is a single bond.
Gotcha.
It took a lot more energy to break that triple bond than the single bond.
Right.
That's what I was saying before. First of all, let's look at a couple things. Triple bond, double bond, single bond.
Right.
Just from the picture, which one's longer?
The single.
Single, right?
Just a little.
Easier to break, less energy. This one's obviously not as long. Why is that? I have how many electrons in here?
2,
How many total here?
4,
How many total here?
6.
There you go.
Oh,
Keep it
takes more
closer.
energy to break that.
Right.
This is basically what you're looking at here,
Sure, the
which is
difference.
why it takes so much. What you saw originally, you were looking at breaking these.
Right.
Okay,
Does
gotcha.
that help?
It's like a thread.
Yeah.
And the
More
O,
threads there are, the harder it is
oxygen
to
would be the
fix.
middle.
You could think of it like that, yes.
That makes so much sense.
This is relatable to the tension affinity and ionization energy, right? In the last chapter.
Not quite.
We are breaking the electrons here, and what you were looking at in terms of electron affinity
It's to share.
is putting an electron into one of these,
Right,
and pulling an electron out would be your ionization energy.
correct. Affinity.
Here I'm looking at breaking a bond, not stabilizing a compound.
Is that because, so I'll probably use that as like when you try to break a pencil, if you have three, it's a little hard to break. Does that make sense?
You can. I mean, because you're saying 3 to break this versus breaking 2 versus breaking 1, I think is what you're saying. You could also think of it as, if I have 2 things around a double bond, it's more rigid, also closer.
Yeah,
Single bond, you could rotate around it,
yeah.
and it's easier.
Was that kind of like a bad analogy, or?
It's okay. However you want to think about it, it's okay. I mean, whatever makes more sense to you is good, as long as it's accurate.
But what happens if you're saying HCl versus ClCl in the analogy of the pencil? Are you be able to tell the
You
difference?
still have one bond.
Correct.
He's just talking about 3 pencils, 3 bonds, 2 pencils, 2 bonds, 1 pencil, 1 bond. That's all, I think, all he's saying.
You would also get energy back too, right?
No,
If you're breaking bonds?
no,
Like burning fire?
no.
You
You're
gotta
putting
apply it.
energy into here. In this context, you are putting energy in to break the bond. That's all we're talking about here. Okay? No matter what, you're always putting energy in to break the bond. Okay? So that's the breakdown.
End of term.
Okay, let's see
You
where
can
we're
apply
at
it.
here. Okay, here, now we're gonna look at something here. What I wanna point out is that you have these 4 compounds here, and these have, this is CH4, CHF3, CHBr3, CHCl3. I'm only looking at breaking this bond here. I'm not worried about the bonds here. There are, remember, 3 chlorines attached here, 3 bromines, 3 fluorines, 3 hydrogens.
Okay.
I'm just comparing breaking the bond here. And of course, it's in the gas phase, because that's when I'm breaking bonds in the gas. Otherwise, I'm not going to be breaking them from a solid. The delta H's at each one forming where you get the H coming off. Of course, it's going to come off more as a gas and other things. We're not worried about that here. We're only looking at breaking this bond here and the amount of energy it took to do that.
Oh, okay.
And you see it varies.
Right.
It varies based on the properties associated with how these other things are all interacting.
Just pulling it more close.
We're not going to talk about the specifics of it,
Okay.
okay? Because it's not going to follow the trends that you want it to follow.
Okay.
Okay, so don't think of it that way. I'm doing that intentionally. The instinct for you is to say, oh, fluorines is going to pull more on this, and you're going to, don't do that. You're not going to find the pattern appropriate here. But what it does mean is that when I look at the overall, and I look at what a CH bond is to break, then it's going to be some average of these. Okay? That's all I'm pointing out here. In other words, they're not all going to be the same all the time. Okay. So there it is. The average bond energy can be calculated. Now, in doing that, that's how all of these were calculated. Okay. And you can see that I have bond energies in kilojoules per mole of each thing. So what was this one? You see 446 to 401.
Uh-huh.
So the average of those that they came up with, CH, is 414. Okay. And that's what these numbers are representing. I want to make that clear, that these numbers aren't representing every specific molecule. They're representing something close to what they should be relative to whatever that was looked at. And then I have the HH, the HC, etc. And now if I look here, these all have different amounts of energy it takes to break them. I look at the CC, it's 347, the double bond CC, 611, the triple bond, 837. So if I clump those in there, you can see CN, C double bond N, C triple bond N, it always goes up in that progression. That's always something that you can solve. If you see something triple bond, it's always going to be more than double, always going to be more than the single relative to itself.
Okay.
And that's what I have here in general. Triple bonds greater than double bond, greater than single bond. That's the pattern, for obvious reasons that we talked about. Okay. This is represented slightly differently than what you're used to because it's not just giving you the formulas. It's giving you, it's emphasizing a bond that's being actually broken. So normally you would see this as CH4 plus Cl2 goes to CH3Cl plus HCl.
But it's showing you.
But instead, it's emphasizing the bonds being broken here. So these are the, or made. These are the bonds broken, these are the bonds made. Certain amount of energy it takes to break this one and to break that one, and a certain amount of energy I get back from this formation and that formation. When the overall is a negative, then I now have an exothermic reaction.
Mm-hmm.
When the overall is a positive, I have an endothermic reaction. So if it's endothermic, these took more energy than I got back, then these were more stable than those. So if I break bonds that are more stable and create less stable bonds as a result, I have an endothermic process. If I
This
break
is
weaker
exo.
bonds and make stronger bonds, I now have a exothermic
Exothermic.
process.
But this is exo.
Well, we got to figure that out. The H of the reaction, the change of the delta H of the reaction is going to be equal to these plus these. These, the delta H, or the H of formation of this, plus this, plus this, plus this. This will be a positive number, negative number, negative number. The overall addition of that will give me the plus or minus for the delta H of the reaction. Okay. I look at the delta H of the formation of each one of those, and then I combine them to get the delta H of the reaction, which is the whole thing. Okay, so let's take a look. Here we go. Delta H reaction, the sum of the delta H's of the bonds broken, plus the sum of the delta H's of the bonds formed. These are going to be positive, these are going to be negative. When the overall is negative, it's exothermic. When the overall is positive, it's endothermic. That's simple. Okay? Okay. So there are tables. It looks like table 9.3 in your text. Let me just put these up. I'll give you a chart, or I'll give you the numbers for you to solve it on an exam. Obviously, you don't have to memorize that. You don't have to put it on your cheat sheet. That's ridiculous. What I have here, if I go to 9.3, or I give them to you, it's going to say that the CH bond is 414 kilojoules to break. The Cl-Cl bond is 243 kilojoules to break. The C-Cl combination is a negative 339 kilojoules, and the HCl combination is a negative 431. I simply say this, plus that, which is a negative, plus that, which is a negative, gives me an overall of minus 113 kilojoules. That is my delta H of the reaction.
It's exothermic.
And that makes it an exothermic reaction.
How do you know that?
Is that okay?
Intuitively, just looking at the bond.
One thing I want to point out that this doesn't do, which is a bad example. Let me see what comes next. No good. Okay. Hopefully we have another example. The reason I say this is because if you had two of these being broken,
Oh, the multiplication.
then you have to multiply that by 2. That's not represented here.
Correct.
You have to put the number that are being broken, multiply it by that number. The number that are being formed have to be multiplied by that number.
Similar to the integrated formation from the other chapter?
Yes, yes. How you do delta H's.
Correct.
Yes.
Mhm.
Additionally, it's not going to show you it this nicely on the exam. I'm not going to give you where they're showing the bond broken. I'm going to tell you CH4 plus Cl2 goes to the other thing. And then you got to determine how many bonds are broken and how many bonds are made. Because I could potentially, if I, let me try this. Let me see what this comes out. I have no idea.
An example.
what is this?
Professor?
CH4,
CO2.
CO2 goes to H3C,
Oh, this is it.
Cl plus
HCl.
HCl. Okay, that's just a one-to-one-to-one.
Professor, there's an example.
Oh, we do have one. Okay, good. Okay, let me get to that example then and make sure that this is clear, because this is important. I don't want to disconnect between how I present it and then what I expect from you on the exam. I want them to be aligned. Otherwise, it's kind of odd to give you something like this, and then all of a sudden you're going to see something different in a more pressurized situation, and then you're going to fail on it. And that's not the point, obviously. Okay, so I hear we're going to get something else, so I guess this is just going to give pretty straightforward. Break chemical bonds always requires energy. Forming chemical bonds, you always get energy back.
Right.
Hence the plus and the minus. Reaction is exothermic when weak bonds break and strong bonds form. Reaction is endothermic when strong bonds break, weak bonds form. Same thing I already said, nothing big there. But here's, when you're studying, you could just simply look at this guide to guide you through whatever we've done. Okay, now let's do the example. So here I'm looking for the delta H. I need the energies from the book. Breaking, bond forming. Okay, here. So they give me these. Okay, good. Okay. This is what you're going to see. So when I look at this, how many bonds broke here?
4.
In the CH4? 4. Okay. So then I say CH4, you don't have this. You're just going to have 414. You've got to identify 4 bonds were broken there. So it's this times 4. Everybody see that? That's important.
Yeah.
Over here, what am I breaking here? An H and an O bond?
4.
And I'm breaking, I have 2 of these, so I'm going to break 4 of those
Right.
HO bonds. And each one is 464 kilojoules. Okay? I'm making 4 H2 bonds. So this is 4H2, and this is a negative, so it's 4 times a negative 436, right? Bonds are forming there, so this is a negative. I'm forming 2 double bond COs. How do I know double bond? I had to make the Lewis structure. If I make the Lewis structure, I see that they're double. Remember that from earlier? We did that C double bond O, double bond O. You'd have to make the Lewis structure on that.
Correct.
So I know I'm forming 2 C double bond O's. Each one is 799 kilojoules I get back. So that means I have 2 times negative this. So 4 times this plus 4 times that plus 4 times negative this plus 4 times negative that. And then I look to see what I get.
170. 170.
Okay, so what is this?
Bigger than that.
So what's 4 times this?
Like, well,
Bigger than that.
Plus 4 times this? And then I'll just say it, make it easier, minus 4 times this, minus 2 times that.
yeah.
Whatever you get, that will tell you what your delta H is, and then if your delta H is negative, it's exothermic. If it's positive, it's endothermic. Oh, here's the total.
Yeah.
So it gives me this, out of all that, you get 170 kilojoules. That means it's endothermic.
Isn't the products first?
Doesn't matter, does it? In this case, it doesn't matter, right? If I make, these are always negative, you're breaking and bond forming and bond breaking. When you're forming, they're always negative. When you're breaking, they're always positive.
Because you have to put energy in to break that.
Because you have to put energy in to break them, and you get energy out
Yes.
when you form them. So
And
it's always the
negative
same.
energy is given to the surroundings.
That's right. That make sense? Okay. Is that all right? No, that looks like it's just 170.
Yeah.
So that means it's endothermic, which is good because now you could try to do this and make sure you get 170. Right? Because I don't have the thing. Okay. Okay, moving on so we can get through this. Bond length. Very straightforward. I've already discussed it a little bit. You can see the bond lengths. They're given in picometer here. So bond length goes like this. As the atom gets bigger, the bond length is going to be larger.
Yeah.
Right? So HH is going to be smaller than HC, which is I guess a little bit bigger than HN. But they're close and there are different anomalies that we don't have to worry about for this. HO, HS, etc. It's just looking at the distance between them, right? Double bonds are going to be shorter than single bonds. This is important. If you have 2 of the same things, your double bond is going to be shorter than your single bond, and your triple bond will be shorter than your double bond. Okay? Those are the things that matter here that you need to know. Do I show that? So here I have triple bond, double bond, single bond. bond length is given here. As the bond length gets larger, the bond strength gets weaker. Okay. So that's the correlation between bond length and bond strength. Once again, nothing phenomenal there. That should be pretty straightforward, and nothing we haven't already had a discussion on today. Okay. The relationship between length, same thing, but it doesn't always hold true. You're not responsible for why. We're not going to discuss it. It's not really relevant at this level. The only thing I want to point out is the longer the bond. So in these cases, you would expect these to be bond length would go up. You get the bond strength should go up, however, or should go down. Longer bond, weaker bond. But here you'll see it doesn't always work that way with individual ones. Not always works with single, double, triple of the same thing, but when you have two different things, nitrogen and chlorine versus nitrogen and bromine, this bond length is a little bit larger, right?
Mhm.
But the bond strength is a little bit larger
That's probably
as
because
opposed to going
the-
down.
when they
It's
bind
how
it.
they're organized within how the electrons are and the lone pairs and everything else that are floating around. The size, bromine's a little bit bigger than chlorine,
Yeah.
and how it bumps in and whatever else.
Okay.
Not responsible for any of that. Not going to even discuss. I just want to make sure it's clear that it's not always exactly the same for these. There could be small anomalies that are not, that don't follow a particular pattern all the time like that.
Why this one? Since
Okay.
the length is
Um,
longer.
Last thing is bond order.
That's supposed to be less.
This is really, really straightforward. Single bond is 1, double bond is
It's because of
2,
the
triple bond is 3.
molecular activity.
Bond order, number of bonds. But what if I have a resonance structure? In the bond order, if I had a double bond
Mhm.
and a single bond in one, and then a single bond and double bond, the overall bond order would be 1.5.
Right.
Why 3?
Wait, what's that?
Wait, why 1.5?
Because it's like having,
It's in between having to look at
right. Maybe illustrating things, sometimes you're like, wow, watch. If I have a single bond, I have a double bond and a triple bond, right? This bond order is 3. The bond order is 2. The bond order is 1. If I have something that has, what was our oxygen here?
Oh,
Bond
Yes.
order, 1.5.
gotcha.
Yes. The illustrations help a lot, right? That's all I'm saying, nothing, right? Because it's only, I have the density going throughout. That would be the same as if I had this, right, versus this. And for those who weren't here, if you label them this way, you're not just flipping them around. You're actually saying that each one has a different one. This is a more accurate structure, which is the hybrid of the two.
Quick question, can you have a resonance structure with a double bond and a little half bond?
Maybe, but I can't think of one on the top of my head. You won't have to worry about it. For example, but yes, maybe. Well, there are always these weird exceptions of things, so I don't ever want to say no, but at the top of my head, I can't come up with one.
You said it was a double bond and
2 double bonds, so you'd have double bond here, and then a triple
And still-
bond. A triple bond with 1 double bond, a triple bond opposite.
Because then it'd be like.
But if it would, it'd be what? 2.5, yeah. If you did, you already would.
Okay.
Okay, so, what are we doing here? So the bond length, 154 picometer for the carbon-carbon, double bond, what, 134, 120, just shows it goes down, okay? What's the point of that?
Recap you?
I guess it's just summary.
Yeah.
Yeah, probably is
Um,
summary actually.
We have this here, okay, here, if you want to look at the bond order, you say total, if you want to do it this way, you can say 1, 2, 3, right? Divided by 2 connections, so how they're going to describe this is the total pair of electrons divided by the total number of bonds. Okay? So it shows total pair of electrons,
There's 3 there.
3 total pairs of electrons,
Oh, there-
and then
oh.
total number of bonds. Remember, it should say how we determine Lewis structures. We say double, triple bonds are all 1,
Yeah.
right? When we determine that. So that's what they're saying here, number of total bonds in between. So we call this 1 and this 1, and that's your 2. I like just saying it's just 1.5. It's pretty obvious,
Yeah.
right? This goes through both, it's just 1.5.
Got it. 'Cause it's that
And they don't get any more complicated than that, that's all it is. It's either 1, 1.5, 2, 2.5, 3, that's really all you can have. It's not like it's anymore. Okay, so now, before we go, really want to finish this, so we have just a couple examples. How would I do this? Consider the molecules N2H4, N2, and N2F2. Which molecule has the shortest N-N bond length? Which molecule has the longest?
And two would have the shortest because it has a triple bond.
N2 would have the shortest because it has a triple bond. That's 100% correct. N2F2 and N2H2. This, let me just put this. This has a double bond. That has a double bond. That has a single bond.
Okay, well then it's that one.
Outside the F, yeah.
The N2H2 would be the longest.
So, single bond, triple bond, double bond. That's what you should be looking at in a question like this.
Correct.
You could do that if you went ahead and did the Lewis structures.
Mm-hmm.
The double bond is here. The triple bond here, single bond. So the single bond is the longest. That has the weakest or the least amount of energy used for bond energy.
Right.
Then the double bond, then the triple bond.
Yes.
Okay. No big deal. What about this thing here? So let me do this. Move this up. Try to do it like this.
The longest one is
So let's try to do this one. What would I do here to fill this in?
Well, there's the only
complete the
bond.
structure already.
How many valence electrons do I have?
Okay, we got 6. We got 5 out 10.
4 plus 8.
We got 10 and
6 times 4 is 24,
Plus 10.
plus 8, plus 2.
So
8.
34 valence electrons.
yes.
Okay. 2, 4, 6, 8, 10, 12, 14. So I use 14.
Double bond in BC.
I have 20 left.
Double bond in the carbon.
2, 4, 6, 8, 10, 12, 14, 16, 18, 20.
A double bond in the carbon.
Okay. Is that good?
Oh, wait,
I feel
what?
like. Why are
Plus
the
5
carbon
plus 8.
Carbon has 3 and 3.
Yeah.
Not good, right? So would I take it from here or from there? Which one?
From
The lower
bottom,
one, right?
yeah.
Here you have more, this is restrained, so I have some rigidity here, so it's not gonna just be able to drop. So these are not chemically equivalent, obviously, because of how they're connected. This one would be the easiest one to donate.
Yeah.
Okay, so let's do that. Let's donate a pair of this here. I like this because I can easily do that, right?
Yeah.
Now that one's okay. What about that one?
Same thing.
Have to do the same thing, okay? So now am I okay?
Yeah.
Okay. Structure, I'm not worried about. I could go formal charge look here, but because of time, I'm not going to waste my time on it. Okay. So now what's the question again?
Complete the Lewis structure and compare the length and strength of the CO bond.
So where are the CO bonds?
So there's one between the C, the OH.
Mhm.
There's one
I have a CO bond here and here,
Yeah, and they also.
And also the other one.
and I also have a CO bond here and here.
And so the top ones have a longer length. than
So I
the
have
single
I have
bond,
two
and then-
CO bonds and I have two C double bond O bonds.
So it's
Let's
longer.
establish that
Yeah.
first.
So short as the bottom.
Okay, so now what does it say? Compare the lengths. Which one's longer?
The
The
single
top one.
The first one.
This one? This is longer. Good. And which one is stronger?
The lower one, the double
Okay.
bond.
And this is stronger.
So more energy.
Is that okay?
Right.
Everybody understand that?
Energy.
Okay, good. We've now finished chapter 9. Next week on Tuesday and Thursday, we'll finish chapter 10. In the lab, you should go halfway through chapter 13 today. That's what we did, right?
Yeah.
And we'll finish chapter 13 in the lab on Tuesday. Then we'll have a lab exam on Thursday. Okay. Have a good weekend. I'll see you guys next week.